Hey guys, your boy Chili here. Welcome back to Hardware 3D. Today's topic, you guys are going to love it. It is shadow mapping, dynamic shadows. People have been asking for this one for a while, and we are going to do it. Let's take a look at what we're going to be making over the next few videos. Here it is, our Sponza scene, and we got these shadows in here, and you got to admit this is some pretty sexy stuff. So I'm going to be taking you guys on a little bit of a journey. You're going to go through a bunch of emotional states. The first state you're going to be in, your state is disbelief. You're like, how is this even done? What kind of magic is this? That's state number one. But then I'm going to explain it to you, and you guys are going to get it, because it's not a super complicated or convoluted technique. It's actually really intuitive once you get how it's done. And you're going to look at this, you're going to think, man, this is cool. This is so elegant, and you're going to feel like a genius for understanding it. The third state is once you get into all the nitty-gritty details of shadow mapping, all the limitations, all the little workarounds and hacks and stuff you have to do to make it look good, then you're going to feel, maybe a little bit unsatisfied, a little bit infuriated. That's phase 3. And then you'll know you've made it. You're now a master shadow mapper. But let's not worry about that right now. That's for the future. In this video, we're just going to look at the theory behind shadow mapping. Now, the first thing I want to say is, well, why? What's the motivation for these dynamic shadows that I've shown? And besides the fact that they look sweet, they give you very important visual cues about the three-dimensional scene that is projected onto the two-dimensional surface of your screen. So look at this thing here. You got this tennis player. Without the shadow, we can see, yeah, he's jumping, but how high? How high? It's hard to say. Is it, is he jumping 3 feet up in the air? Is it only 3 inches? If we had a shadow being cast, that would give our brain a lot more information to decode what this scene is actually telling us. Without that information, it's all up in the air. So the first question we should answer here is, what is shadow? What is the shadow that we're talking about in the shadow mapping technique? Well, shadow, shade, that is just the absence of light. When things are lit, then they have, we can see their color. But when they're not lit, they are dark. And they are then, in shade. We could say they're in shade. So you might say, well, Chili, don't we have that already? Here's the scene I have here without the dynamic shadow mapping here. And we see, look at the backside of this thing here. Look at these curtains. They ain't lit, fam. But, so we already have shadows. Well, it's complicated, right? We have a kind of shadowing. It's built into the fundamentals of our dynamic lighting here, our shader. They call it a shader. I've said this before. They call it shader. That's a dumb name for it. It should be called a lighter, right? Because it's lighting things. And so in our lighting calculations, we obviously, things that face the light, they can receive the light. Things that face away from the light, it is impossible for them to receive photons from that light source. And so by not being lit, they are shaded by default. But facing away from the light source isn't the only thing that can prevent it from being lit, right? If there is something in between a point of matter and the light source, if there is something in between, an occluder, then that point won't be lit. So because these legs are here, they should prevent the light from, reaching the points on the floor here behind the legs. That's the kind of shadows that we're talking about. These are shadows that are cast by objects, basically objects that occlude the rays of light coming from our light source. But in our system here, when we render, when we quote unquote shade each of our meshes, we consider those meshes in isolation. So when I'm shading this floor here, all I'm considering is the floor itself and the light source. I'm not considering anything in between, and therefore it is impossible for me to get those dynamic shadows, those shadows that are cast or thrown from one object onto another. So now the question is, how do we do it? How do we get objects to, throw shadows onto other objects? And the answer comes, think about shadow puppets, the ones you make with your hands. You've got some kind of a light source like a projector. You put your hands in front of that, and you can project shadow silhouette objects onto a flat surface like a screen. You look at that and you say, well, there is some kind of a link, some kind of a parallel there with projection, like the kind of projection that we do when we normally render a 3D scene. Obviously, there are large differences between the kind of, screen projection that you do when you're rendering a scene and the kind of projection of projecting a shadow from one object onto another object. With this one, you've got a flat surface that you're projecting onto. You're just working backwards from points in the world and projecting them onto this scene here. There's your viewpoint, your focal point. With the projection of a shadow, your focal point is the point of the light source, and you're forward projecting that from some object in front of the light source onto some other object behind that object, both of which are likely not going to be flat. It's a much more complicated problem, but there's enough similarities that there may also be similarities between the techniques. A wise cat once said, "Everything the light touches, it's lit, fam." And he's right. Whatever the light sees, like if you were to view the world from the exact position of the light, whatever you could see from that position means that there is a clear line of sight between that point and the object that you're seeing, which means that there's also a clear line for photons to travel, which means that that point is lit. So take a look at this scene here. Clearly, there are dynamic shadows being cast by the objects in this scene. Now let's look at this scene, but from the point of view of the light. Here it is. Can you see any dynamic shadows? Try and spot the dynamic shadows. Trick question, it's impossible, you can't see them. Because we're viewing from the point of view of the light, everything that we can see, the photons are also reaching, and thus we cannot see any of those shadows being cast. I can scan around here, no matter where we look, not a shadow to be seen. But if we switch back to a different camera, there's the shadows again. So I think you guys know where I'm going with this. Obviously, the way you do this to be perfectly correct when for dynamic shadows is only ever render the scene from the point of view of a single light in the scene, and then you're never going to be wrong. Because there aren't no shadows. They just don't exist. How can shadows be real if our eyes aren't real? Think about it. Okay, now I'm just getting in some reports of some demanding, selfish people who want to render from points of view other than the light source. Very rude. But, okay, so maybe rendering from the point of view of the light won't solve our problems, except it will solve our problems. Rendering from the point of view of the light gives us all the tools we need, and it is gosh darn orgasmic. So here's what we're going to do. We're going to render the scene from the point of view of the light. And what that's going to give us is that's going to give us actually a map of everything that the light sees. Now, here's the trick. We're not going to render with color. We're going to render the depth values of every pixel that's rasterized. So for every pixel in our rendering surface, we are going to render the depth of the object that generated that pixel. So instead of our render target storing, 4-component vector, RGB, and then a fourth value, it's going to store just single components, just depth. Every pixel is just a depth value. So if we were to blow this up and, graph the values, we're going to see, well, at the edges here, like let's say this point here, the depth is going to be this much. So I don't know, let's say that's this much. And then it is going to be, it's going to be going further out. So it's going to be linearly increasing up to a point. And then it's going to jump down because we have this point here. And then it's going to be getting closer and then further. And then it's going to jump back up and it's going to be going like this. So this is the graph of values across this one-dimensional surface here, projected from a two-dimensional scene. Now, when we render the scene from the camera's point of view, what we're actually going to do is refer to this shadow map here to determine which pixels are being lit by the camera and which pixels have their light source, their path to the light source occluded. By the way, let's see what it looks like when we render depth from the point of view of, well, here I'm looking at out of the light Let's render the depth from the point of view of the light. So here's what that looks like. You see close objects, very dark. And as you get farther away, they're lighter and lighter. Now, when we're rendering an object from the point of view of our camera, let's say we're rendering this wall here. And it's a simple geometry, has a couple of vertices. Those are going to be transformed into screen space. And, some attributes are going to be interpolated as you rasterize them in the screen space, in the pixel shader. Maybe there's texture coordinates and, maybe there's normals or coordinates into a normal map. But often you also interpolate like the world position of those vertices. So in our pixel shader, for each of these pixels in our surface, they correspond to some point on the geometry that we're rendering. And we have the position of that geometry in world space in our pixel shader. We use that for lighting calculations and so forth. Sometimes it's world space, sometimes it's the view space of the camera. It doesn't really matter. The point is we have the position of these objects. Now here's the interesting part. What if I take this world position and I apply the transformation matrices from the projection from the point of view of the light? So I apply those matrices that will project this point onto a point on my rendering surface here, which is, my light map or my shadow map, I should say. So I can transform this and get a coordinate that I can use to look into the shadow map. Okay, what's good about that? Well, this transformation will give me two things. It will give me the position in the shadow map, and it will also give me the depth relative to the camera. And let's say this depth is D is equal to 0.5, doesn't matter. So I know this point is 0.5 away from the camera. And if I look up into the shadow map, I can get the depth of the thing at that same location that the camera saw. So the camera saw this. It has a depth here, and let's say this is just 0.05. So the thing that I'm looking at from the perspective of the camera, when transformed into the light's frame of reference, we know that the light saw something at that same position in its view frame. It saw something that's much closer. So it didn't see this. So this must be in shade. And there you have it. You render from the light's point of view. You capture this map of depths. And then when you're rendering from the camera's point of view, for every point that the camera sees, transform that into the light's frame of reference. You get the depth from the light. You compare that to the recorded depth that the light actually saw. Call this DR or whatever. And if D is greater than DR, then the thing that you're looking at was not seen by the light. There was something in between, and therefore it is shaded. It is not lit, fam. That's it. That's all there is to it. It's a very elegant solution. It's a very cool technique. I like it a lot. All right, so from this we understand now we've got to do, two passes. First, we got to render from the point of view of the light source. Capture the depth data, the light map, which is really, it's basically just a lookup table for ray casts from the point of view of the light. So in a sense, it's like we're casting rays and building up a discrete lookup table of depths. And once that render pass is complete, then we render from the point of view of our camera as usual, only one difference. Before we do our lighting calculations and everything, our diffuse, our specular, we first transform this position into the light's frame of reference. We do the lookup into the shadow map. And if it fails, if the depth that we're seeing is much farther away than the depth that the light saw, then we just skip it. We say, okay, cool. We don't have to do our diffuse. We don't have to do our specular. We don't have to look up into our normal map. None of that stuff. We can skip it all. Obviously, this puts a bigger strain on our system now. We've got to do another pass of rendering. And later on, you'll know that you generally don't get away with just one pass when you're generating your shadow map data. But anyways, you've got to do more rendering passes. There's good news, though, and that is this one obviously it doesn't need a complicated shader. It actually doesn't need a pixel shader at all. You can bind a null pixel shader and just capture the depth data. Very simple vertex shader, no pixel shader, and it will work usually. Another interesting thing to note is, like I said before, there are many similarities between the projection you use for rendering and the projection that you use for throwing shadows, right? Which is the same, and that's why we use projection and rendering for generating our shadow map. And the projective matrix that we use is a perspective matrix, because if you've got a point light here, it is, I mean, the rays of light are diverging like this. So it's the same idea as the idea behind, the pinhole camera and the projection and so forth. It's the same mathematics of similar triangles. One little implementation note here is when you are rendering as normal and you multiply your perspective matrix and then you output that from the vertex shader, the rendering pipeline is going to divide W. It's going to do the perspective divide for you. So your pixel shader values are going to be all perspective divided. But when you are manually transforming a point from world space into light space at the time that you're rendering from camera, then you're going to have to do that perspective divide yourself manually. Note there's an exception to this. For point lights, yeah, it's perspective. But for a directional light, you actually don't use perspective because these aren't diverging. There's no similar triangle geometry involved. So for directional light, like for example sunlight, you would use an orthographic matrix, and then you wouldn't have to do the manual perspective divide here. You could skip that if you wanted. Or you could just, divide by W in either case. And for, an orthographic matrix, W will be 1 and nothing will happen. But yeah, let me just go over quickly the flow of the steps, the things that you got to do. So first thing you do, rendering from the point of view of the light, you bind a camera matrix that is from the position of the light, pointed in the direction that you want to capture the shadows in. For every object that you draw, the pixel shader is going to be the same. It's going to be a null pixel shader. Don't bind a pixel shader. Vertex shader, very simple. All it's going to do is, transform the points of the geometry with the model view projection, and you're done. You render that. You don't bind a render target. You only bind a depth stencil. And then once you're done, you're going to have your depth stencil texture. It's going to look something like this. For shadows, I don't even allocate bits for stencil. So instead of 24/8, I just allocate full 32-bit to depth because you don't need the stencil. And that gives you a little bit more precision. Then when it comes time to render the actual scene itself, you bind your render target, you bind your depth stencil, your normal depth stencil as usual, and you render. You make sure your vertex shader is supplying world coordinates. That'll be interpolated and fed into the pixel shader. Then in the pixel shader, you got to bind some extra things. Obviously, you got to bind the shadow map to the pixel shader so the pixel shader can look up into the shadow map. And you're also going to want to bind matrix for transformation from world space into the screen space of the light. So in your pixel shader, then you can take the world space of the point of the pixel being rendered, you can transform it by the view projection of the light, bring it into light space, homogeneous coordinates. Then you manually divide W, do the perspective divide. That'll bring you into NDC space. So that means that all the points that you're rendering, if they map to something within the view frustum of the light, they will be, between -1 and +1 in the X and the Y. And the Z will be between 0 and 1. Now, when you want to look up into this texture has texture coordinates. So it has Y down and 0, 0 at the top left. So you have to transform this into UV coordinates, which is just, very simple, multiply by 0.5 and then add 0.5. Once you got that UV, you can look up into here. You can compare with the Z from the NDC, which corresponds to this Z here. Look up into here, which corresponds to this Z here, and you do your test. And then Bob's your uncle, you got it. Now there's a few optimizations that you can do here. You can push some of that work that I described from the pixel shader up into the vertex shader, and I'll show a little bit of that in the next video. But there's one very important issue that we have to look at here. All right, so one problem that we haven't really touched on yet is, okay, so we're rendering the scene from this point of view, right? We're going to look up this point that we're rendering in the shadow map. So we map that to the shadow map, and it maps to a point outside of the shadow map, which makes sense because when we rendered from the light's point of view, this was outside of that rendering range. So we won't get any dynamic shadows here. We'll have to do, a special check and say, okay, if you try to map this and it's outside of the NDC range, -1 to +1, then just ignore it for the purposes of shadow mapping. But I mean, obviously that's not what you want. For rendering a shadow, if this is a point light, it'll be weird for it to only cast shadows in a certain direction. If it's a spotlight, then that works fine, and that's how you would do it. But for a normal point light, you can't just get away with one render. You actually got to render from a bunch of different perspectives. So you'd render from here, and then maybe you'd also render from here. I mean, I didn't do a great job of drawing it here, but in general, if you want to render a scene omnidirectional in all the different directions, you basically got to render it, like this. 4 directions and then up and down. So you'd have to render, for every light, you have to render it 6 times. That's a lot of rendering. So what you'd really like to do is, cut down on it as much as possible. For example, look at this shadow map render here, and you'll see if we render the full range of the view frustum, we're also rendering these objects. But these objects can only throw shadows over in this direction, which is out of the view of our camera. So there's no point in rendering these. So I mean, first of all, when you're rendering frustums, if an object is outside, you usually want to clip it. Don't even process it. We're not doing that yet, frustum culling, but we will be doing it because it's a huge optimization. It's just a no-brainer. But what you also want to do is clip your frustums to each other. So we know that anything beyond here isn't going to affect the scene in terms of shadows. So we can basically, clip this frustum to something like this. So instead of drawing this whole thing, we can reduce the frustum to here and then clip anything that's outside of that reduced frustum. And that reduces the amount of work that we have to do. For this one here, what would we want to clip to? Well, you might say, well, this is outside of the scene, so we don't have to draw this. But that's not true, because even though it's outside of the view of the camera, it could still throw shadows onto something that is in the view of the camera. So you can't clip things in front like this, but you could clip to the frustum like this and this. So I don't know, maybe your clipped volume then would be something like this afterwards. And that might exclude objects here, would exclude, this and this. You get the idea. So what we're seeing here is that every pass is going to go over different geometry. And what that means is that we can't just go through the entire scene graph in one pass. If you remember, the whole architecture that we created, maybe this isn't a very good one. The whole architecture that we created for the render graph, with the techniques and the steps, the idea was we can go through this scene graph. We only have to pass through it once, and we can render all the different passes. We don't have to traverse the entire scene graph for the normal rendering and then traverse it again for the silhouettes, for the outline. One run through the graph and it submits jobs to all the different passes. But that's only if we're rendering from the point of view of a single camera. If we're rendering from multiple points of view, then when we do the frustum culling, we're going to have different traversals of the scene graph depending on what camera point of view we're rendering from. So because all the traversals are different, we can't do it all in a single pass. So what we want to do is we want to traverse through the render graph from the point of view of, one of the shadow cameras and submit to certain passes. And then with a different traversal, we want to submit to different passes. So what we're going to do is we're actually going to create a little system, a channel system. So what we're going to do is every technique, or maybe every step, I haven't decided yet, but every one of these is going to have a list of channels that it is active on. And then when we traverse through the render graph, we're also going to have a list of channels that we're broadcasting to. And only if those channels match is the technique going to be processed and it is going to be submitted. So if we have a technique that is, for generating the shadow map in the shadow pass, then that technique will be active, but the other techniques won't be active. They won't submit. Then in the normal pass, the shadow map technique will not be active. Only the normal ones will be active and only they will submit to the job queue. And the way I'm going to do this is very simple, just with bit masks. So 64-bit number, that gives us 64 channels. So when we traverse through the scene graph to do one pass through, we give it, a mask, which might have multiple bits set. This is the filter, and that will get ANDed with the filter stored in the technique, let's say. And when you AND those together, if any of the bits match, that means that that technique will be active. You'll see it in the code in the next video. There's also another reason why you want to cull your frustum when you're rendering from the point of view of the light, and that is bringing the far Z in closer gives you a better precision on your depth values, which is going to give you, less artifacts when you actually render the shadows. So that's another benefit of, reducing your frustum for your shadow map render. But yeah, I think that's gonna about do it for this video. In the next video, we're gonna go over all the steps that I did when I implemented the shadow mapping in code. We're gonna see how it's actually implemented in C++ and DirectX. And it's gonna be a good time. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, it helps a lot. And I will see you soon with some more Hardware 3D.